So, Jai Hind, myself Ritesh Sharma, EN Department, Ajay Kumar Garini College. So, today I am here to discuss the subject of the energy science and engineering. The subject code is KOE033, in which we will discuss first the unit number 1, and the topic is the energy and its uses. So you can see that the topic which we will going to cover in this lectures are the introductions, units and scales of energy used, then mechanical energy and transport, and then in last we will discuss the heat and thermal energy. So these are the topic which we will discuss in this lecture. So first of all, what is the forms of energy? Or you can say in the very beginning, we start with how we are using these energies. So not all the energy that we are using is electric energy. We all know that the energy that we are using is not all in the electrical. So what are the other forms of energy that we are using, or how they produced? So these are the things which are very, very important as far as the initial based. And when we consider all the forms of energy in our disposal today, we can group them into some categories. What are those categories? Let us see. So first of all is, you can see that these are some forms of energy like oil, coal, natural gas, and we collectively call it the fossil fuels. So we can see all these things in our surrounding or in the nature. Another forms of energy is like the solar, hydro, wind, biomass, biofuel, geothermal, ocean energies, and we also call them as the renewable energy. And another is a nuclear energy. So these are some energies that we have using as a electric energy. Ultimately, we are getting the electric energy for the use. So now let us see compare the relative these types of resources or energies like fossil fuels. You can see here, we can see that the fossil fuels energy, that is around the 78%. Okay, then we have the traditional biomass energy, which is around, you can say 9.1. This is the data of the 2015 actually. Then we have the biomass, geothermal and solar heat energy, that is around 4.2%. Then we have hydro, then wind, solar, geothermal, biomass, these are the renewable energy, and then biofuel as a transport. And ultimately we are getting the nuclear energy, which is very, very least, around 2.3%. Okay, so these are some forms of energies basically that we are using in the year 2015. Now, starting with the primary and end use energy, how we are using this energy in the primary form and end use energy. Like the understanding energy used in the country is not an easy, because you can see that how we are first side. For instance, some forms of energy like cooking gas, we are using it as a direct. Okay, we are using directly. We are using the fossil fuels and like that. But other forms such as the electricity are produced from other forms of energy, like such as diesel. Okay, and diesel or gases, natural gases. So we call it the crude oils. Then, to simplify this one, there is a need to categorize energy into those available at the starting point of the energy chain, and those are actually used by the energy consumed at the end of the chain. So let us see a flow chart for that and how this energy are using as a primary and end use energy. So first step, we need to obtain a more holistical conceptual framework for energy use in the country. Let us that we begin by some questions like, what are the sectors of economy that require energy? Okay. Then what are the forms of energy that requires, so what are sectors that we have to think about the sectors which are required this energy. Almost all the sectors which require the energy, but we have to categorize them actually. Then what are the forms of energy that are required, and then how these various forms produced. So we have to think about and we have to get the answer of these questions. And the sector of economy are required energy have already been broadly identified, like residential, commercial, industrial, transportation. These are some big sectors which are in any countries. So the industrial sector is really very quite complex, and it include large subcategories of the agriculture, mining as well as manufacturing. The forms of energy that are available on the global market are the best categorized into the primary and the end use energy. So we can categorize them primary and these are the primary and these are the some end use energy. So this is the transformed through the various process to end use energy for final consumption. So that is a transformed through the various processes so that the end use energy for final consumption. We are using like electricity. The most important example of the end use is the electricity. You can see that this is the most important example, and this is usually provided by electricity utility. So who generated from the mixture of fossil fuel, nuclear fuel and renewable energy. So the energy which is being produced and which is finally used by the utility. So these are the some examples. The energy process involving starting from the primary energy resources and its transformation and final use in the form of end use. So we have some flow chart. We can see that how these can be transformed. So first you can say that from the total primary energy supply is there. Okay, that is whatever fuel is there. If it is imported, then like diesel, petrol, kerosene, and we have some fossil fuels also, and that is being converted or processed. So oil refineries, thermal power plant, hydro power plant, some power plant, so that it can be converted again to the final user. Or we can directly use for some purposes like kerosene, LPG and like that. So this is how the energy conversion takes place from primary to final consumption. Some more facts about how we use more and more energy. So you can see that energy use per person is increasing year by year. So you can see that from the graph it is increasing year by year, and the world population is also increasing linear in that ratio actually. So the global energy use, if you take the data from the resources are limited, but we are using this global energy and it is increasing like that. So from in the 2010 it is around 480 exajoules actually, 480, but now in 2020 it is around, if you take the current data or the latest data, it is around 648 exajoules. So we can see that if we are use more and more energy, that means the resources are being exploited. So now we need to find an you can say that alternative way to use these energies. This is the data as far as the 2019, the total energy consumption in India. In our country, you can say that this is the percentage of the energy or resources that we are consuming. Like coal, the coal is being used 45%. The petroleum and other liquids are 25%, biomass 20%, natural gas is 6%. So around you can see the 70 to 75 plus we are relying on these fossil fuels. Then we have hydro, nuclear and other renewable resources. So this is a scenario as far as the total energy consumption in India. So now if you look at the global energy consumption, it is around the same, like the coal is 27, natural gas 25, oil 33. Then here the renewable is 5%, you can see. Nuclear energy is 4%. So this is the data which is latest data to 2020, and it is the primary global energy consumption by 2019. If you look at the sector wise, if you know the sector wise consumption of the electricity in India, like for example, it's industry, it is 44, agricultural for 18%, domestic 23%, commercial 8%, and then traction and railway other. This is how the sector-wise consumption of the electricity in India. Okay, so total consumption you can see that is the 948,228 gigawatt hour. So this is the number of units that we are consuming. Now, after this introduction, because this introduction is important, because how much energy that we are consuming and what is the scenario, this is very important. Now, we will go to the units and scales of energy use. Different units, different scales that we are using. That, like, in general, if we say that these are the units or the MK system that we usually adopt actually. Okay, so if here the charge is represented by coulombs, you can say, current in amperes, and potential in volts, resistance in ohm, temperature in Kelvin. So from here, we derived units are energy is used in joules, power in watt, pressure pascals, force in Newton. So these are the some energies that we already familiar about this in our +2 courses. Okay, so we have to understand more about these energies like power, energy, pressure, force. Okay, so these are some derived unit actually. We call the derived unit. Now let us start with this some basic concept like the how like the speed. Speed is given by meter per second charge, and according to the Newton's second law, this force can be derived by mass and acceleration. So mass and acceleration is LT square. So we can derive this unit of the force. From force, we will get the energy, that is kinetic energy, that is half mv square. So half mv square, if we put the values over there, mass for m, v velocity is meter per second, that is L square upon T square. So it comes out to be 1 joule, which is equivalent to this, that is mL square by T square. So the unit, if we talk about, is the unit of this is of energy is mL square T square. That is mass. Energy is mass into velocity. If we look about the kinetic energy. Okay. Now let us verify this unit of energy from other aspects. Like power that we have. Power is equal to, this is the energy per unit time. And if we look at the energy here that we have already found, mL square by T square into 10. So that is equal to kg m square s cube. Okay, that is joules per second. The power is given by joule per second. So from here, joule is equal to V into T. So joule means energy can be equal to your watt into time. So energy, that is energy is given by watt into time from this. So energy in one time. Now we have the pressure. The pressure is force per unit area. The force, again, we have calculated the force. Previously, we calculated the force kg m square s square. From here, we put the value of force per unit area, that is L 1 by L square. We will get the expression for the pressure. That is 1 Pascal is given by 1 Newton per meter. Now the different forms of energy, that is not a debatable question. We have also we know that the energy, there is a law of conservation of energy is there. Okay, so that means we know that the energy is just changing its form. Okay, it will not disappear. It is just changing its form, like from kinetic to potential to chemical to thermal or some rest energies. So the conservation of energy, a single number characterizing a system or even each part of the system that can be traced through time and as it flows and changes. Okay, and its unit, we can say that its unit is mass into L square by T square. It is all these different forms of the same units. The different forms of energy must have the same unit, as we have also we can see. Like for example, kinetic energies can be determined by using this expression half mv square, where mass is the speed square. You can say this is the unit for that. Similarly, if you find the work and potential energy, that is force into distance, we can find the work ml square by T square, and again with that work by pressure. That is again when we apply the pressure that is P into V is the pressure into volume, that is pressure is the force per unit area and volume. So pressure again we can say force per unit area into volume. So this is the expression for the work done in case of this volume and the pressure. Again, for the thermal energy, that is if we calculate the energy in case of this heat. So this is expression, well-known expression, where the N is the number of moles you can see, R is the gas constant, T is the temperature. If we apply this, put all the things, like for example, this is the 1 mole is there, joules for energy, joules per mole into Kelvin. This is the unit of R is the gas constant into K, that is T, and it comes out to be mL square T square. So here the heat basically thermal energy is responsible basically by the kinetic energy of the molecules, make it as a heat, appearance as a heat, you can see here. So these are something like Kb is the Boltzmann constant, its value is this, and T is the temperature in the Kelvin. So this is the thermal energy, and I can say that the energy is very much equal to mL square by T square, the same with here. Now we come to this electrostatic energy, that is Q into V. Q is the charge, V is the potential, and here the electrostatic potential, that is electric field, that is for force, and the force does work on the charge and its move. Okay, and you can say that in SI unit, what potential you have to move 1 coulomb of charge through, or you get or to lose 1 joule of energy. That is comes from this. The volt is joules per coulomb, and if you can apply this divided by seconds, so joules per second is watt and coulomb per second is current. So watt per ampere. So from here you can say simple power is given by, this is volt, this is ampere, so V into I. So that potential that we are applying over here. In case of quantum energy, we know that there is a well-known expression of E is equal to h mu. Okay, where h is the Planck's constant, v is the h mu is the frequency, and the energy of 1 quantum of light photon, which can be calculated by this. So E, that is energy, which is given by this, h is the Planck's constant, frequency 1 by t, and this is the, you can see that this is the unit of Planck's constant h. This is the different frequencies. If we change the frequency, obviously that energy level will be changes. This is the value of h, Planck's constant. And the Einstein rest energy is given by this. So if we apply over here, they will get the same expression. So these are the certain units and scales that we are going through in our syllabus. Okay, after that units and scales, we will come on this mechanical energy and transport. The basic, you can say the elementary mechanics is basically responsible or relevant for understanding the transport. Okay, like kinetic energy and potential energy. So if we are talking about the mechanical energy, that is the kinetic energy and potential energy. And we are also interested in its transport. Okay, because when the object is in moving, or whenever there is a spring is there, its displacement and its direction. Okay, both things are very important. Like this kinetic energy is, you can see that when the mass of a body m moving at the speed of v. So this is the well-known expression of the kinetic energy. Similarly, the potential energy means with its, you can say, the energy stored in the configuration of the object interacting through the forces. Whenever you can mgh, whenever there is a height at a certain height h, okay, having some mass, so it stores some energy. We call it potential energy. This example is given to you. There is a motion against the force, that is the wall is going. So whenever the kinetic energy is when it converted over the potential energy, that is at height h, it is given by mgh, where g is the gravity, that is a gravity constant, 9.8 meter per second square. the force point in the direction of decreasing the potential energy, that is motion in the direction of force, that is potential energy, is converted to the kinetic energy. When the motion in the direction of the force, it means the potential energy is converted to the kinetic energy. Another example is given by the spring. When there is a spring is there and the spring stores energy, and that is given by U is equal to half kx square, where k is the spring constant and x is the any position, at what position it is there, how much displacement is given to the spring. So after this mechanical energy and transport, heat and thermal energy. So what is basically heat? Heat is the transferring thermal energy, that is from high temperature to the low temperature. Okay, so heat, that is when it transfer of energy from high temperature to the low temperature. It is the natural way of the transferring the thermal energy. The thermal energy, the total energy from the relative motion, excitation of the particles above this temperature, absolute zero, that is the 0 Kelvin. And many particle systems like micro kinetic energy, that is a thermal energy. Suppose if you're talking about this closed vessel and it is an isolated vessel, we have particles are there, and if they are energized or excited, so that means it heated or it transfers some energy. Okay. So how the heat is transferred? The question arises that now we have the three modes of transfer of heat, like the conduction, convection and radiation. So in conduction, what is basically, as you can see on the picture, the example, the pan is on this heater is there. So what is going on here? The conduction is there. When the pan is got heat, and you can say that the heat energy is transferred, that is in the solid. So when heat energy is transferred in the solid, it means it is a process of conduction. So it is a mode of conduction is conduction. The convection, you can say that where these are the fluid in the pan, there's a water or some fluid is there. The energy is transferred, the thermal energy is transferred through these in fluid particles. This is convection. And the heat is going in the radiations in the outer surface. It is the radiations. So let us look into that. So what is the conduction is? The conduction is defined as the process in which heat flows from objects with higher temperature to the object with lower temperature. Okay, this is basically we are talking about in terms of solids when it is in higher to lower temperature. As area of higher kinetic energy transfer thermal energy towards the lower kinetic energy area, okay, high speed particle clashes with the particles moving at the slow speed. As a result, slow speed particles increases their kinetic energy. This is the typical form of heat transfer and takes through the physical contact. So it is always taken in the physical contact. The conduction is also known as the thermal conduction and heat conduction. So this is called proper conduction is there. Some examples, we have a lot of examples as far as this, as we have seen over this picture also. This is the example. Another example, you can see that the ironing of the cloth is the example of conduction where the heat is conducted from the iron to the cloth. It's a physical contact over there and or in solids. Another example is the heat is transferred from hand. If you put the ice cube on your hand, that is the heat is transferred from body to that cube, and the ice cube will melt. The melting of the ice cube when heat in the hand is there. And heat conduction through the sand in the beaches, it can be experienced during the summers. The sand is a good conductor of heat. So this is another example of the conduction. Now the convection is there, in which convection, the movement of fluid molecules from high temperature region to lower temperature. Means the heat is transferred or heat energy is transferred from high temperature to low temperature, but in fluid or gases or liquid. Like the boiling of water, okay, that the denser move to the bottom while the molecules which are less denser move upward, resulting in the circulation motion of the molecules so that the water get heated. So that in the water particle, there's a water is heated, that is the denser, the molecules that are denser move to the bottom, while the molecules which are less denser move upward. Okay, so this is how it moves actually in the circular motion in the boiling water. The warm water around the equator moves toward the poles, while cooler water at the poles moves toward the equator. So this is why, because of the convection. Blood circulation. The blood circulation, the warm-blooded animals takes when with the help of convection, thereby regulating the body temperature. So this is also very helpful as far as we have to keep the body temperature. Now the next term is the radiation. What is radiation? The thermal radiation is generated by the emission of electromagnetic waves. So here the electromagnetic waves is there. Now the radiation is generated by the emission of the electromagnetic waves, and these waves carry away energy from emitting body. That is whatever energy which is emitted by a body, and these electromagnetic waves carry these waves. Okay, and the radiation takes place through the vacuum or the transparent medium, which can be in either a solid or liquid. That could be a solid or liquid. Now, thermal radiation is the result of the random motion of the molecule in the matter. Movement of this charged part, electrons and the protons, is responsible for the emission of electromagnetic radiation. So this movement of the charged electrons, protons is responsible for the emission of electromagnetic radiations. Example of this radiations, this mode of the heat transfer is microwave radiation emitted in a oven, is the example of radiations. Another is the ultraviolet rays coming from the sun, is example of radiations. This is also example of radiations. Release of alpha particle during the decaying of the uranium-238 into the thorium is also example of radiations. So this is the example of the examples of radiations as a monoconductor. So these are the how the heat is transferred. These are the different ways: conduction, convection, and radiation. These are the things that we have to study in this lecture. So this is the lecture number 1. So thank you so much.